There are two types of nucleophile substitution mechanism depending on the structure of the haloalkanes. They are known as SN1 and SN2 mechanism. The letter S here is the abbreviation for substitution, while the letter N is the abbreviation for nucleophilic. The number 1 denotes a first-order unimolecular reaction, while the number 2 denotes a second-order bimolecular reaction. Consider the hydrolysis of 2-bromo-2-methylpropane. So the reaction will proceed by SN1 mechanism, which involves the two steps. The first step is the formation of the carbocation, and this reaction is slow and therefore determines the overall rate of reaction. Okay, so since the carbon here is partially positive and the halogen is partially negative, so the bonding here will break unsymmetrically where bromine will get both electron, and this will give us a tertiary carbocation. Right, so here this carbon will get the positively charged. This one is a tertiary carbocation, right? And also the bromine will become Br minus, which is our leaving group. So since tertiary carbocation is the most stable carbocation, so no need to do any rearrangement, right? So let's proceed to the second step. Since the carbocation form is very reactive, it will react rapidly with the nucleophile to form the organic product. So in this case, since our nucleophile is a weak nucleophile, which is water, right? So one of the lone pair on oxygen will make a bonding with the carbocation. So here it will form a protonated alcohol. Okay, so since here we just need the OH group, so we need to remove one of the hydrogen here. So we are going to react it again with water molecules. Right, so react it again with water molecules. So one of the lone pair on the oxygen here will make a bonding with the H plus, and then the bonding here, alright, will goes to the oxygen as a lone pair. Okay, so this reaction also a fast reaction, and it will give us our organic product, which is alcohol. Okay, and also the H3O plus. Okay, so here we have the H3O plus. Okay, so this is the hydrolysis of the tertiary haloalkanes with water. If you use a sodium hydroxide or potassium hydroxide aqueous solution, let's say we use the sodium hydroxide aqueous here, we will still get the same product, which is our alcohol, alright? But on the second step, for the nucleophilic attack, our nucleophile from the sodium hydroxide aqueous solution is only the OH minus group, the hydroxide ion. Okay, so the OH minus, alright, will attack our carbocation. Okay, and then we will get straight away our organic product, which is the alcohol. Okay, so it is differ from the reaction with water, where for the reaction in water, first we will get a protonated alcohol and then react it again with water, then we will get our product, which is the alcohol. Okay, but then if you use the sodium hydroxide aqueous solution or potassium hydroxide aqueous solution, we just take the OH minus ion as our nucleophile for the step 2. Okay, and then straight away we will get our organic product. Okay, so since this is a first order reaction, okay, it is a unimolecular reaction. All right, so for the first step, okay, the rates it depends on the concentration of the haloalkanes only. Okay, so the concentration of our nucleophile does not have any effect on the rate of reaction. So this implies that the hydroxide ion or the water, okay, in our previous mechanism is not involved in the rate determining step. So that's why in step 1 there is no nucleophile involved in this step. In the SN2 reaction mechanism, the process of bond breaking and bond forming occurs simultaneously. For example, in the hydrolysis of the chloromethane in a sodium hydroxide aqueous solution, the mechanism will involve only one step. Right? So to show the SN2 mechanism for this reaction, we are going to draw it in a 3D form. Okay, so let's focus on the carbon and chlorine bond. Alright, so we are going to draw the carbon and chlorine bond first. Alright, and then this is a solid line, and then we have another solid line here, and here we have a wedge line, okay, to show the bond in front, and another bonding here is a dash line, wedge dash line to show the bond in the back. Okay, so since this carbon is attached to the chlorine and another three bonding is the hydrogen, so put the hydrogen, all right, in this three bonding, okay, and the nucleophile. Okay, so since we have the sodium hydroxide aqueous solution, so actually our nucleophile here just take the hydroxide ion. So take the hydroxide ion, right? So since the carbon is the electron deficient side, okay, so it has a partially positive charge and the halogen here has a partially negative charge. Okay, to minimize the repulsion between the halogen atom and also the hydroxide ion, the hydroxide ion will attack the electron deficient side of the carbon from the back, and the bonding between the carbon and the halogen will break. Okay, so this is what we call the bond forming and bond breaking occur simultaneously. So this reaction is a slow reaction, right? And it will form a transition state as an intermediate. Alright, so our intermediate, the transition state. Alright, so here we have a partially negative charge and partially negative charge. Don't forget the symbol of double dagger to indicate the transition state. Okay, and label our transition state. Okay, and then here, right, we have a fast reaction where the product formed here will be an inversion of configuration since our nucleophile, our hydroxide ion, attack the backside of the electron division, okay, which is the opposite side of our halogen atom here, right? So we are going to show the product here in form of inversion configuration. So it is much like a strong wind inverting an umbrella. Okay, the configuration of the product is inverted relative to the configuration of the haloalkanes. And also here we will get our chloride ion. So since the hydrolysis of the chloromethane is a second order reaction, and this means that both the chloromethane and also the hydroxide ion, which is our nucleophile, is involved in the rate determining step, which is the slow step here. A species with a negative charge usually is a stronger nucleophile than a similar neutral species, except for the acetate ion. Since in SN1 reaction, the nucleophilic attack occurs after the rate determining step, hence the strength of the nucleophile has no effect on the rate of an SN1 reaction. Okay, so for the SN1 reaction, it can be either weak nucleophile or strong nucleophile. But in SN2 reaction, the rate determining step involves the attack of the nucleophile on the haloalkane. Thus, a stronger nucleophile is needed for the SN2 reaction. The order of reactivity in SN1 reactions depends on the stability of the carbocation form. Since the tertiary carbocation is the most stable carbocation, thus the tertiary carbocation has the highest reactivity towards SN1 reaction. And since the methyl halide form the least stable carbocation, it can be considered to be unreactive towards SN1 reaction. In SN2 reaction, the methyl halide react most rapidly and the tertiary halides react slowly, that they can be considered to be unreactive. The important factor that determines the order of reactivity in the SN2 reaction is the steric effect. A steric effect is one in which the rate of chemical reaction depends on the size or spatial arrangement of the groups attached to or near to the reaction site of the molecule. So in this diagram, we can see the metal halide and also the primary alkyl halide is the most unhindered, and it is easier for the nucleophile to attack the backside of the electron deficient carbon. Alright, compared to the secondary and tertiary alkyl halide, the tertiary alkyl halide is the most hindered, where it will make nucleophilic attack from the backside of the electron deficient carbon more difficult, and it will slow the reaction rate. In order to identify whether the reaction will undergo SN1 or SN2 reaction, we have to consider these three things. The first one is the type and reactivity of the alkyl halide, where the primary and the metal halide will favor the SN2 mechanism. The secondary alkyl halide, it can be SN2 or SN1 mechanism, while the tertiary alkyl halide will favor the SN1 mechanism due to the steric effect. Second thing is the strength of the nucleophile. Since the SN1 reaction does not involve the nucleophile in the rate determining step, so for the SN1 reaction, it can be either strong or weak nucleophile. But for the SN2 reaction, since the nucleophile is involved in the rate determining step, so we have to use the strong nucleophile for the SN2 mechanism. And last but not least is if we have other information from the question. For example, if the question states the rate of reaction or the products form or anything else. So this is a summary of the difference between SN1 mechanism and SN2 mechanism. For the SN1 mechanism, the kinetic rate of reaction is proportional to the concentration of the haloalkanes only, since it is a first order reaction. While for the SN2 mechanism, since it is a second order reaction, the rate of reaction is proportional to the concentration of both haloalkane and also the nucleophile. So the reactivity of the alkyl halide for the SN1 mechanism is tertiary is greater than secondary, secondary greater than primary, and the metal halide is the least reactive towards SN1 mechanism. While for the SN2 mechanism, the metal halide is the most reactive towards the SN2 mechanism, followed by primary and followed by secondary. So the tertiary alkyl halide is unsuitable for the SN2 mechanism due to the steric effect. Next, the effect of the nucleophile. Since the nucleophile does not involve in the rate determining step, so the nucleophile strength are unimportant in the SN1 mechanism, but the strong nucleophile are required for the SN2 mechanism because it is involved in the rate determining step. The intermediate form in the SN1 mechanism is the carbocation, and for the SN2 mechanism is the transition state. So since the carbocation involved in the SN1 mechanism, so the rearrangement may occur to form a stable carbocation, but in the SN2 mechanism, there is no rearrangement occurs. Now, let's have a look at an example of how we are going to determine which one is the most reactive towards SN2 and SN1 reaction. So we are going to circle the best choice of each statement. So before we do that, let's identify our haloalkane. Okay, so this is our halogen, right? Halogen, halogen, halogen. Okay, so since here, this is the carbon that bearing the halogen, it got only one alkyl group attached to it. Same goes to here. This is the carbon that bearing the halogen group, it only got one alkyl group attached to it. So these two compounds are a primary haloalkane or primary alkyl halide. Okay, but since this one is a bulky group, we have a bulky group here compared to this one. Okay, so the bulky group here makes it difficult for the nucleophile to attack the backside of the electron deficient carbon. Alright, so since we have a bulky group in this compound, okay, even though these two both are the primary haloalkane, right? So this one is going to be the compound that is most reactive towards SN2 mechanism because it don't have a bulky group, which is the steric hindrance. Okay, it is easier for the nucleophile to attack the backside of the electron deficient carbon. All right. So for the second one, okay, so here we have the halogen. Okay, so we have only one alkyl group attached to it. So this one is a primary haloalkanes. Okay, for this one, this is the carbon that bearing the halogen. So we have two alkyl group attached to it. Right, so this is a secondary haloalkanes. Okay, and then here, all right, so this is the carbon that bearing the halogen. Okay, so there is no alkyl group attached to it. So this one is the metal halide. Okay, so we have a metal halide, primary and secondary. So the one that is most reactive towards SN1, okay, that will form the most stable carbocation, okay, between these three compounds is the secondary carbocation. Okay, so the secondary haloalkane here will give the most stable carbocation compared to primary and the metal carbocation. So this one is the most reactive towards SN1 reaction.